Okay, thank you, Alan. Thanks for the opportunity to present sort of an overview of the field I'm looking into this 11th North American meeting of the Calcite Society. This overview will be rather personal, as you might guess. I'll make a few disclaimers at the outset. You hear me in the back? Should I do that? How's that better? Everybody's fine. Okay. A few disclaimers. I'm going to be talking about work that I find very interesting, and therefore it won't be necessarily comprehensive. And in particular, I'm going to be stressing transformations that occur at single metal centers. That is, I won't have much to say about those recent advances in cluster chemistry, although I don't mean by their omission that they're any less significant. So let's start out. I've noted an increased interest in alkane activation during the last 10 years. And also, we've been refocusing from the interest in olefin hydrogenation and isomerization to olefin polymerization reactions. That is, we've moved away from making CH bonds to processes that involve making carbon-carbon bonds in organic metallic chemistry. For better or for worse, there has been in academics and also in industry a reduced interest in CO hydrogenation chemistry, syngas chemistry in general, although there still are a number of people actively pursuing this area, as I know from the abstract books. But in general, I think the interest has died off in the last 10 years somewhat. There is a rapidly growing interest in reactions related to oxidation. Organometallic chemists normally are interested in reductive processes, and so this new interest in oxidation using organometallic complexes is quite notable. And so we're starting to see organometallic complexes that are well-defined, X-ray structures and so forth, that contain oxo, peroxo, and oxo type ligands. And there's a corresponding interest in organometallic chemistry of these other heteroatoms like sulfur and nitrogen also emerging. There are also a number of developments in homogeneous chemistry, homogeneous catalysis and organometallic chemistry where one can start to draw some analogies to oxide-supported organometallic compounds. Fortunately, for many of you, I won't have much to say about this, although I do know this is a major thrust where alkoxide, silox type ligands and the like are being used to mimic supported transition metal compounds as catalysts. And finally, I point to what I call a physical organometallic approach. And just as organic chemistry grew initially by synthesis, structure, and later by more physical understanding, so too is organometallic chemistry growing, now to a point where we're beginning to investigate in detail the mechanism of various fundamental transformations, those that are common to a large number of reactions. And also, surprisingly, we're just now getting to the point where we know with some confidence the values of metal ligand bonds associated with energy. And these are very important, of course, in making predictions about thermodynamics associated with fundamental steps. Okay, so let's jump into the alkane area. Although there was some early work by Chad and later by Coleman that pointed to oxidative addition of carbon-hydrogen bonds in an intermolecular sense, certainly in the last 10 years we've seen a number of new workers join and show that in general, E8 16-electron complexes of the type shown here in the center are capable of oxidatively adding unactivated carbon-hydrogen bonds. That is, even methane will oxidatively add to these bonds centers. They're generated in a variety of ways by glycolysis of dihydrides, for example, with expulsion of H2, glycolysis of metal carbonyls with expulsion of carbon monoxide, and even by thermally heating these alkyl hydrides, one can generate these metal fragments which will oxidatively add new CH bonds or force go back to where they were formed. These are highly reactive centers, as I said, almost all of them may be classified as D8. And these strong donor ligands like phosphine and cyclopentadienyls greatly favor the D6 product, which has the alkyl in the hydride attached to the metal center. And an oxidation center, oxidation state 2 higher. So these donor ligands seem to be the key to the stability of the alkyl hydride. I'll give you an example of an especially well understood system explored by Jones and Baird, where they found this methyl cyclopentadienyl rhodium methylphosphine methyl hydride compound could be prepared by various synthetic procedures and shown to be unstable, losing methane at minus 17 degrees centigrade. This is one of those Da 16 electron fragments. This compound readily adds substrates like benzene to make this methyl hydride compound. He studied the thermodynamics of this process. To apologize, this arrow is pointing in the opposite direction. He measured the activation energy for expulsion of benzene, and also this interesting process which goes to an eta-2 or pi-bonded aramine complex, which proceeds with a lower activation energy than the process leading to complete dissociation of benzene. And on this basis, Jones and Baird have argued that aramines are especially susceptible to this oxidative addition because they can form this pi complex precursor to the fully oxidatively added product. There's an alternate way to activate CH bonds that's been explored with the early transition elements and some of the lanthanide and actinide elements as well, with these workers shown here. These involve no redox, and so these really could be viewed as either four-center exchange or, as I've been calling them, cyclobond metathesis type processes, where R and R prime, which can be a variety of carbon-based substrates, are exchanged between the early transition metal center and a hydrogen atom to form a new alkyl, the new octane, for example. Heather Marks has been interested in the ultimate hydrogenation properties of these catalysts. Of course, there we must couple an insertion step with one of these sigma-bond metathesis type processes. And these can be very fast indeed. In fact, Marx has shown these are among the most active olefin hydrogenation systems known. The interest is in how these CH bonds are activated at a metal center where no redox can occur in a formal sense. Our group has been interested in these methyl scandazine systems, and here I show the current observations we've been able to make. Again, we always see exchange of R and R prime between scandium and hydrogen. We never see, unfortunately, the scandium hydride product and the CC coupled alternate. Nor do we see the microscopic reverse, namely activation of the CC single bond by these things. As I'll show you a little later, we know how some of the thermodynamics compare in these kinds of processes, and I can tell you that the thermodynamics actually favor the alternate, that is, to make the scandium hydride and CC coupled product. As I said, that's never observed, so there must be a strong kinetic preference for the metathesis reaction proceeding as I've shown. Another thing of note is that the stronger CH bonds are activated more rapidly than the weaker. The more atmospheric in the CH bond, the faster the reaction. Some of these reactions occur to only a partial extent, that is, we reach an equilibrium situation, and this kind of an equilibrium is very nice because there you can estimate with considerable accuracy the relative values of the scandium, in this case the scandium phenyl, and the scandium hydrogen bond, if you know the enthalpy of the equilibrium, and of course H2 and infinity CH bond associated energy. Some of them proceed very far to the right, like this one shown here, where the methyl compound reacts with the phenyl compound and methane. Here the equilibrium lies so far to the right that we never see any starting material. Based on a number of experiments and some calculations by my colleague Bill Goddard, the picture of the mechanism that emerges here is that shown at the top, where the metal carbon bonded species, for example, the methyl scandazine methyl, interacts with the CH bond. And here we're going to see a recurring theme I'll point to a number of times, where carbon-hydrogen bond-paired electrons acts as a donor to the metal center. Here with an early metal, a very electrophilic, acidic metal center with a vacant orbital, we envision an initial interaction of the type shown here, where this electron pair is simply delocalized to some extent into the vacant orbital on the metal. We go through a symmetric transition state with lots of dotted lines that has this geometry, according to Goddard, method where this angle is very open. Goddard points out that transition metal centers here are very good at doing this because if they have lots of d orbital character in their bonding to carbon centers, due to the local extensions of d orbitals, they point nicely to both carbon centers, and there's lots of bonding in the transition state, and this metal is a transition element. Likewise, hydrogen wants to sit in this very open position in the transition state, and so, and because it has a non-directional 1s orbital, it again has good overlap with the carbon center. And then we simply back off in either of the two directions from the symmetric state, and we've affected the overall transformation. The simplest possible mechanism you can think of seems to be completely sufficient to explain the observation. These alternative transition states, which would affect the CC coupling reaction, would necessarily place carbon with its more directional orbital in that crucial simple place, and thus there's less bonding, and this transition state is much less stable relative to the one shown here. If we step back now and ask what can you do with these systems that activate CH bonds in terms of functionalizing alkanes, alpine, and the like. I think at this stage it's fair to say that we've had disappointingly few systems show any kind of activity toward anything other than simply doing the transformation that's shown. We would like to couple one of these CH activating steps with some other process that would insert some functional group into the CH bond. But as it's been found with these low valence systems, any group you would like to insert into the CH bond reacts more readily with these metal centers that do the CH bonds. I don't think the activator poisons the metal center toward the CH activation process. What we can do is rather trivial, I guess, and to some extent trivial. We can affect CH activation with deuterium exchange. For example, we do a benzene. Crabtree and Belkin have shown you can use sacrificial olefins to take hydrogen away from alkanes to make it olefins. And I guess the most notable successes are from Bill Jones's group again, where he's shown that you can affect a few turnovers of this transformation shown here, where he has affected an intramolecular insertion of this nitrile group into the carbon ruthenium bond generated by activating the methyl group on this area. But this runs only a few turnovers and then dies by some process that's not really fully explored. Crabtree has recently reported using what the physical chemists had discovered several years ago, namely that unexcited mercury atoms are capable of affecting H2 extraction from alkanes and affecting CC coupling reactions. And by devising the proper setup, Crabtree has shown this can be quite useful in affecting certain CC coupling reactions. Again, with expulsion of H2. These are fill reactions that are driven by light. I think Bergman was the first to look at the microscopic reverse of these CH activation processes, namely the reductive elimination process. And here I show a rather unexpected result from Bergman's lab, where he looked at the cyclohexyl hydride decomposition to cyclohexane, and in the presence of benzene, capture of the iridium-1 fragments to make it from hydride. The surprise was that when he carried out the appropriate kinetic deuterium isotope study, he found an inverse that is less than 1 kHkB. That normally signals a stepwise process, and the process that seemed most consistent with inverse effect was the one shown here, where the CH coupling process initially leads to an alkane, in this case cyclohexane, coordinated to the iridium center by means of a CH bond. And so here again we have one of these things now called a sigma complex, where a sigma pair of electrons acts as its donor to a metal center. Since deuterium substitution here would affect shift in the free equilibrium toward the sigma complex, we see a faster rate for the overall process, where the rate limiting step is, believe it or not, pushing off CH bond from the metal center. The return back to the alkyl hydride system seems to be faster. In support of that, Bergman found that you can see Hg exchange in the type shown here. Again, you find that there is a methane atom of iridium that mediates this exchange. Jack Morton's group also found a similar inverse KD in a tungsten system, in this case the methyl hydride, where he was capturing the low valent tungsten product with acetonitrile solvent and generating methane. And again, in our system, a little bit cleaner system, he was plagued by a bimolecular scrambling process that obscured some of the features of the reaction. In this fully methylated tungsten methyl hydride, we see the clean process where there's intramolecular tracking. That is, one of the 30 CH bonds of the ligands oxidatively adds to the tungsten center to make this product. And the results are, again, indicative of a stepwise process involving one of these sigma complexes, the methane atom, tungsten C in this case. Earlier studies of reductive eliminations from things like platinum alkyl hydrides had shown normal kinetic return isotope effects, that is greater than 1 values. And so one might wonder whether alkane atoms, these sigma complexes, mediate all reductive elimination. And by reversibility, again, all oxidative additions would be mediated by a free coordination of the CH bond of the alkane to the metal center, and then a full oxidative addition will make the product. Well, it's come to our attention that all of those systems where you see a normal KD that is greater than 1 are those where it's downhill to make the low valent metal center and the alkane. Those centers where you see an inverse KD, it's endothermic though to affect the overall transformation. If one makes some reasonable assumptions that these barriers for forming the sigma complex are not too different, then you can see that the rate limiting step here in these exothermic systems would be forming the sigma complex, and you would expect a normal KD in those systems. And in those where it's highly endothermic, in those centers where the reaction proceeds spontaneously in the other direction, the rate limiting step again is rather unexpected, but must be pushing the CH bond away from the metal center. And in those cases, we would see an inverse KD if it is as shown there. So the bottom line I'd like you to take away is that these sigma complexes seem to mediate not only reductive eliminations, but oxidative additions, and they seem to be present even in the sigma bond metathesis way of activating CH bonds to the extent that there must be a vacant orbital on these early metals to coordinate the CH bond. Now these sigma complexes are really not all that unexpected, given the fact that Kubas has isolated analogous types of complexes as stable materials that can be examined by X-ray crystallography, neutron diffraction, and the like, where the AH bond of the dihydrogen atom is intact. Only a tenth of an angstrom longer than that for AH2. These have lower AH stretching frequencies, and they've been found in a number of cases now. I would say the number is growing daily almost, where one can identify what used to be thought to be a dihydride as in fact one of these dihydrogen atoms. They're commonly found with these 6 metal centers with either a cationic charge or electron acceptor type ligands that would retard the tendency for the metal to fully oxidatively add, that is, raise its oxidation state by 2. So these plus charges and electron efficient nature of the metal center in general tends to discourage the full oxidative addition. You can think of these as being sort of arrested oxidative addition. Crabtree has pointed out that the close proximity of the 2 hydrogen nuclei and greatly shortens the P1s and the NMR for these metal hydrides. And he's used this criterion to estimate HH distances in a number of polyhydrides and shown that many of these are likely to be dihydrogen atoms rather than polyhydrides. These sigma complexes are also similar to the intermolecular arrangements noted by Green and Brookhart and Agostic pH interactions in metal systems. This comes from Homer, the Greek word for clutching for oneself. You know, Malcolm Green, you won't be surprised if you adopt such an obscure term to describe these kinds of CH interactions. These have now been found in a number of cases And they're not all that unusual, really. You can think of them as being three-center, two-electron bonds, very similar to the arrangement that we have in diborane, in transition metal boron hydrides, and even in these bridging hydrides, especially the early transition elements, where again we have these electron pairs, in this case of metal hydride, in this case of CH electron pairs, donating to a vacant orbital on the metal center. Brookhart went further and pointed out that these systems, when you have agostic interactions, especially the beta-agostic interaction, are likely candidates for olefin polymerization catalysts. So where he found, he made some very reasonable arguments about when one might expect olefin insertion to be favored, and in fact, although there are a large number of olefin hydrides that do not do olefin polymerization, those that have agostic interactions are now found commonly to affect olefin polymerization. In this case, he actually went to the lab and found a system and showed that ethylene insertion proceeds with this particular ethyl complex. Our group has been exploring from the andesine system, as I said earlier, and the ethyl compound does indeed have the beta-agostic interaction in its ground state, and these systems are very active ethylene polymerization systems as well. Interestingly, we find that the rate of insertion of ethylene into the scandium carbon bond is a very strong function of the group R on scandium. For example, the second order rate constant reported here at dry temperature for the hydride, not surprisingly, very fast. But there's a very interesting order here for the alkyls, with the propyl complex being roughly 15 times faster at inserting ethylene than is the ethyl complex. So that's what is intermediate. Interestingly, the ethyl complex has a beta-agostic interaction in a stable form, and the propyl has a normal structure, almost certainly because there would be necessarily a bad steric interaction between the methyl group and one of these non-methyl CPs in the propyl group. So the features that encourage olefin insertion are really the electron-deficient nature of the metal, and the beta-agostic interaction is simply reflecting that. But in fact, the implication here is the scandium system that the beta-agostic interaction actually interferes with the olefin insertion step, and presumably that CH bond must be associated before ethylene is inserted. Our system is only one of several what I could call well-defined homogeneous Ziegler atom olefin polymerization systems. Most of them have been effective with ethylene, much less effective with other alpha olefins. Jordan has described these cationic, they're tungsten alkyls with non-coordinating X minus counterions. Marx, Turner also has explored these. Marx has looked at the methyl analog of the zirconium system as well as the thorium system, and found some very active systems for ethylene polymerization. Our system is isoelectronic, but it's now neutral, and we don't have this counterion to contend with. They're not as electrophilic because they don't have the plus charge, and so they're not as general as reactive as some of these cationic systems, but nonetheless have proved to be useful in studying the fundamental steps of ethylene polymerization. And we have, as I showed, studied this K1 process and the overall polymerization process. We've also found at higher temperatures chain transfer by beta hydrogen elimination to release the alpha olefin and also compete. We've examined some of the features of this beta hydrogen elimination process by rapidly trapping the hydride as it's formed with its more reactive substrate, the butane, to make this unreactive to butene product. With just a few equivalents of 2-butane, you can find zero order added to butane, find that its top K1 step is very limiting conveniently enough. And we've examined the effects of beta substituents on the rate of beta hydrogen elimination. I think the clearest picture is here in the Apple series, where you can see electron releasing groups accelerate, electron withdrawing groups decelerate the rate of beta hydrogen elimination. Not surprising, I hope, given what I told you about the scandium center. It implies size, the polarity in the transition state is very much like that shown here, with this electrophilic scandium center ripping a minus off the beta carbon, applying substantial positive charge buildup in the beta carbon. Sort of carbonium ion-like transition states seem to be prevalent in these early low electron division type systems. With these kinds of rate constants in hand, one can predict, should be able to predict, molecular weight distributions for oligoethylene. Although I'm sure you can't see up here, it says for methylscandazine propyl plus 6.9 equivalents of ethylene at dryest temperature, where we have effectively no beta hydrogen elimination occurring, only olefin insertion. And we can assume that the ethylene insertion into the propyl is the same as into the pentyl and so forth. So chain initiation is the same as propagation, and so we should in fact have a living ethylene polymerization system under these conditions. By quenching the alkyl products with methanol and examining the oligoethylenes by GC analysis, we see here in this fraction, which is roughly C13 through C39, there are two things of note here. One is we only get the I carbon over alkanes, straight chain alkanes, again implying no chain transfer has occurred, because if we did beta hydrogen eliminate, the hydride ethylene insertion would start an even carbon chain oligoethylene process. And so no chain transfer appears to be occurring on that basis. Furthermore, you can fit the molecular weight distribution. Here we have 4.2 equivalents consumed, but you can see you can satisfactorily fit into a simple Poisson distribution, assuming that you have a living system, and importantly, all the scandium centers are active. It's not hard to find an organometallic system that will polymerize ethylene. In fact, many will, but defining exactly what's doing the polymerization is often very difficult, even in a homogeneous solution. You can find that a very minor component of your system can be doing all the polymerization. This system, when gets to 4.2 equivalents consumed by knowing how much ethylene has been polymerized, and also by knowing how much scandium you have there. And I hope you can see that the fit of that type is only possible if most, not all, of the scandium centers are acting alike. Interestingly, with the methyl, where chain initiation is slower than propagation, we would expect a shift to higher molecular weights and a broadening of the oligoethylene distribution as the system, which inserts early on, consumes a disproportionately large amount of the ethylene relative to starting material, so we get this broadened distribution. Well, ethylene polymerization is nice, but of course it would be best to be able to polymerize a number of different types of olefins. Unfortunately, this single bond metathesis, the CH activating process I described, is the dominant process when you go to any olefin other than ethylene. That almost certainly is due to the unfavorable sterics associated with bringing the pi orbitals of the olefin up to the front two orbitals on the scandium center. One bad interaction with one of these bulk helices is assured. And so the olefin turns and approaches this equatorial plane with the CH bond, and that's just the reaction centered at the carbon-hydrogen rather than this carbon-carbon double bond. Well, if that's true, if we take some of the sterics away, maybe we could see some chemistry of alpha olefins with these scandium alkyls. And so we prepared a number of less crowded versions of these scandium. And here I show you the results from a system that's been tied back with a silicon bridge to open the way. What we find is indeed alpha olefins do react by a process other than single bond metathesis. In fact, they are nicely dimerized and very highly selectively dimerized in the case of butene to this head-to-tail version. This is entirely expected if one simply argues sterically. The olefin insertion into the scandium hydride bond would be expected to produce a less crowded terminal alkyl. And all this may go on many times before a second olefin insertion occurs. If that olefin insertion does occur, now we have a beta-beta disubstituted carbon here. You know, the transition state electronically wants to be carbocation-like, or ideally suited for beta hydrogen elimination at that stage. And of course, second insertion is this favor on stereogram relative to very fast beta hydrogen elimination here. And these kinds of selectivities, I think, reflect that very strong preference for beta hydrogen elimination in these systems. We can think about coupling the two olefin centers together, that is to examine alpha megadienes, and indeed these cyclizations to the methylene cycloalkanes are, in many cases, remarkably effective. Okay. More recently, our group has been exploring even less crowded centers where we substituted one of the cyclopentadienyl groups by an amide, tertiary phenylamide in this case. And here we can prepare hydrides of the type shown here, which can be crystallized and shown to have these electron-deficient bonding arrangements, much like diborane, or double hydride bridge supporting this kind of structure. This compound reacts with alpha-olefins not to produce dimers as in the scansine system, but instead to produce relatively high molecular weight oligomers. Now, we've examined this process in some detail recently, and we find exclusive head-to-tail coupling is known, and by examining the oligoproteins, we've been able to show that there are essentially apactic polymers being produced here, as you might expect, given that we have no particular asymmetry associated with that scandium center. Again, we've looked at the oligomerization of propene in some detail to show that all the scandium centers, again, are acting in the same way. And again, we can get satisfactory fits at low conversion where chain transfer is effectively not happening to these theoretically Poisson distribution. Again, supporting the hypothesis that all the scandium centers are acting alike in the system. A different type of polymerization has been explored by my colleague Mark Russ in his group, and a nice summary of these recent advances in what he calls ring opening metathesis polymerization, locking, has appeared in Science. These polymerizations depend not on olefin insertions of carbon bonds in the conventional way that I talked about in Ziegler-type systems, but instead take advantage of catalysts that affect olefin metathesis. And these have now been well shown, have been convincingly shown to involve methyl-carbines and metallocyclobutane type intermediates. And of course, if one starts with a cyclic olefin, you can affect polymerization, like shown there. Krauss has explored, at least initially explored, some of these titanosine metallocyclobutanes as precursors to the catalytic system, entering from the metallocyclobutane part of the metathesis scheme. And probably if one introduces strain of metallocyclobutane, for example, using this precursor, you can affect polymerization to give monodispersed polymers, the type shown there. There are a couple of mistakes. This is double bond should not be a double bond. Single bond bracket should really extend out there. But the point is, one gets monodispersed systems that are living, and in fact, you can add more warning drugs to a higher molecular weight, or more interestingly, add a different cyclic olefin, and prepare not only end-cap polymers, but block copolymers with monodispersed segments. This group have also explored the synthesis of conducting polymers by aromatase cyclooctapentane, and impressively with some new ruthenium-type catalysts, explored the preparation of functionalized polymers by aromatase and functionalized polymers. Okay, the next part of the talk, I'd like to shift gears and talk briefly about organometallic chemists' interest in oxidation and related processes. This has traditionally been a coordination chemist and a biochemist placement to research. And in fact, they have shown that a number of systems, mainly transition metal porphyrin-type complexes, are effective catalysts for converting alkanes to alcohols using oxidant sources such as peroxides, peracids, and idosylbenzene. In fact, I believe on Thursday there is a session that will focus this conference on these kinds of processes. Some of these same complexes will affect the oxidation role of this as well. I don't have to tell this audience how important it would be to find a very selective catalyst for introducing oxygen atoms into simple molecules like methane, or even carrying out partial oxidation that would couple low molecular weight hydrocarbons like methane to heavier ones. As an organometallic chemist, I ask questions that are related to things I know about, and to the extent that oxine is like a carbene center, and dioxygen is like ethylene, one might ask, what does it take to get an alkyl group to migrate to an oxide organometallic complex, or to a peroxide hydrated related system? Organometallic chemists are also asking questions about hydrodesulfurization and hydrodenitrogenation. This has been almost exclusively the domain for heterogeneous catalysis. Very few systems that I'm aware of show clean carbon-sulfur bond cleavage, or for that matter, clean carbon-sulfur bond formation in a clean homogeneous organometallic model system. Again, we can ask questions about what it takes to migrate carbon centers to and from sulfur or nitrogen. And many of these complexes are just now beginning to be prepared and the reaction chemistry explored. Our group has been interested in reactions of phenolphthalein alkyls that are generated from these more stable alkylidine hydrides or olefin hydrides by either alpha or beta hydrogen transfer. To get these very reactive D2 16 electron phenolphthalein alkyls. My group is now doing the unheard of for organometallic chemists, throwing water and dioxygen as organometallic compounds. And in many cases, transformations occur that give very clean products. For example, this oxyl hydride is cleanly formed from virtually any of these in water. Surprisingly, this is the first oxyl hydride that's ever been isolated. It seems remarkable to me, but I think that's a true statement. And when you think about it, it is surprising that you would have an oxidizing group like an oxyl hydride reducing group next to each other in complex. Same kind of complex can be formed with H2S or ammonia. So these seem to be very facile processes indeed. You can affect oxygen delivery to these with oxygen donors like nitrous oxide or tertiary butyl hydroperoxide. Perhaps most surprising is that dioxygen simply traps the alkyl to make a stable peroxide complex. With methanol, we get very clean transformations that involve loss of methane from the methylene hydride and formation initially of this formaldehyde hydride derivative of phenolphthalein. This is reversible. You can show that by dynamic NMR techniques and also by trapping the methoxide with simple lithium-ICO or methyl isocyanide. Now, on heating, once these transformations occur, which involves carbon-oxygen bond cleavage to give this oxo-methyl group that described a minute ago. Interestingly, when we substitute these three hydrogens with deuteriums, we see an inverse case, again, a signature of a stepwise process, almost certainly involving this hydrogen transfer that we know is going on, and then a rate-limiting carbon-oxygen bond cleavage. This is, of course, exactly the opposite of what I'd like to do. I'd like to do the microscopic reverse. And we're probably never going to do that with an early metal center like Canada. On the other hand, with sulfur, we might like to break that bond, and indeed, exactly analogous chemistry happens with methane thiol as it happens with methanol. Here's a great example of how Kinbrel can come to the rescue. You simply go in and change a few atoms and copy the same file again, changing a few of the numbers like the inverse isotope effect. But again, analogous chemistry, and here we are doing a very clean carbon-sulfur bond cleavage reaction. We're now asking questions about the stereochemistry of the migrating carbons, the kinds of questions that physical organic chemists often ask about transformation. With this peroxide alkyl that I described earlier, we find the expected chemistry in terms of oxidation of triphenylphosphine to triphenylphosphine oxide. We found no oxidation of styrene, however. But we did find when we added styrene, we got a very clean transformation that did not consume styrene. And after a while, we traced that observation to the catechol, the tertiary group catechol, that they add to styrene to stabilize it against polymerization. Indeed, we purposely add weak acid to show that you can catalyze this carbon-oxygen bond forming reaction that occurs with OO bond cleavage to give this oxo-alkoxo product. Our thinking is that this involves initial protonation of this distal oxygen. That encourages the alkyl migration to the oxygen in the OO bond cleavage, resulting hydroxide deprotonates with the product. Indeed, we have found other examples that fit the same scheme where we now think that alkyl migration to peroxide oxygen is slow in the absence of electrophilic promoters. And the function of the electrophilic promoter is to encourage alkyl migration in a heterolytic sense, that is, into the sigma star orbital of the O bond here. And that would, of course, imply that electrophiles would encourage that pair of electrons to heterolyze towards the positively charged oxygen, and then we can close the catalytic loop. We see terrific acceleration of some of these processes by added electrophiles. I think any catalytic oxidation of an alkane is going to have to involve a fundamentally different scheme. We're just now beginning to see some transformations of this type. And these are now calling 1,2 addition elimination processes involving some metal X double bond with some YZ single bond substrate. And of course, in this case, I'm talking about metal oxo and the CH bond of an alkane. If one could affect this transformation, and I'll show you there's some reason to think that might be on the near horizon, then one would generate an alkyl hydroxide with a sufficiently high oxidation state on the metal. One might even hope that reductive elimination of the alcohol could ensue. Of course, there's no reason at the outset to discard this alternative way, but I'll show you at the top that the top way is this time the way that seems most likely based on pressure. We found that these 1,2 addition elimination reactions occur in some cases to the exclusion of the more traditional and more expected things like alpha, beta processes, 1,2 addition, reductive eliminations and the like. For example, when we take this oxohydride species I described, where we label the oxygen with O18 and treat it with deuterium oxide, we see a remarkable thing happen. We see oxygen exchange occur, but the metal hydride bond does not exchange. That rules out any process that involves alpha hydrogen migration to give a hydroxide. Because any scheme you can think of from there on would certainly introduce deuterium in the hydride position. Instead, we think a simple addition of the OH bond of water, the O bond in this case, to the metal oxide bond gives us this hydroxy hydride, which again can't reductively eliminate, or we would see scrambling of deuterium into the hydride position. It must undergo the 1,2 elimination process faster than any kind of reductive elimination. Well, water isn't very impressive, but what about CH or H2 bonds? In the case of the amide, the NH system, this is isoelectronic to the oxohydride, if my treatment with D2 affects exchange of the hydrogen on nitrogen with deuterium without exchanging the hydride position. Again, a little surprise. And that implies, again, these 1,2 addition elimination schemes must be going on to the exclusion of these processes involving migrations, oxidative additions, reductive elimination. It also demands that the D2 addition to the tantalum nitrogen double bond occur as shown here, not there, because that's symmetric and would affect exchange of the hydride position as well. The most impressive work, I think, has come from Bergman and Wolzansky's labs, however, where they found that this 16-electron zirconocene analog, this mido derivative generated by loss of methane from this amide alkyl, or by association of this dimeric structure, will activate the CH bond with things like benzene, 1 and 2 addition to make a nice product. In a Wolzansky system where again you have bulky groups and auxiliary ligands, he's found that methane, in fact, is even activated in this fashion. is the organometallic chemist's recent interest in measuring bond strength. This has happened during this decade. There's been a concerted effort by a number of groups to try to get good hard numbers for metal carbon bond strength. Perhaps most notable in this group of early workers is Halpern, who studied the homolysis of metal carbon bonds, especially of cobalt and manganese. These are necessarily rather weak bonds in order to observe this process at all. And he was able to show that in many cases these bonds are just barely strong enough to make the complexes isolate. Halpern has been a proponent of the steric influence on the bond strength. And in fact, there are some data to support that. Reaction calorimetry is something that might come to mind if you'd like to measure bond strength, because after all, that's how all the bond strengths in many of the bond strengths in organic chemistry have been derived. But in fact, combustion is not a very reliable way to get bond strength in organic metallic chemistry. Of course, organic metallic compounds contain metal centers, and these make oxides on combustion. Oxides of different crystalline forms, different degrees of crystallinity. Given the very large lattice energies for metal oxides, these can lead to very irreproducible results. Nonetheless, in solution calorimetry has been carried out by Connor to give some reliable bond strengths. Some of those are shown here for simple halogenation of metal carbon bonds to make the alkyl halide. Much more extensive study has been undertaken by Mark's co-workers at Northwestern, where they have carried out a number of reactions. One shown here, for example, where tertiary butanol is used to hydrolytically cleave the thorium carbon bonds to make alkane and the thorium oxide. And if one uses the average of the thorium oxygen bonds and thorium oxides as benchmark, then one can get absolute bond strengths that are as reliable as that estimate that Mark has used there. But certainly the relative numbers are much better, and you can see here these are now much stronger bonds than those I showed for Halpern and Connor's work. These are quite respectable bonds by any standard, single bond. Together with Henry Grinza at DuPont, our group has investigated a different way to get bond strengths. It gives only relative bond strengths, but it gives quite accurate relative bond strengths. And it's this sigma bond metathesis type equilibrium that's been used here with ruthenium and platinum-2 complexes. The surprising finding was that for a whole variety of these kinds of reactions, the equilibrium constant approximately 1 was found. That tells you that a number of things. First of all, it tells you that whatever makes HY a strong bond makes YZ a strong bond by the same amount. That's a surprising finding. For a variety of different axes, oxygens, carbon, nitrogen, we find that correlation holds quite nicely. Here's a graphic way of representing that. There's some notable deviations from the line. Cyanide, which we have multiple bonds, does in fact make a stronger bond than this correlation would predict. Hydrosulfide also forms a stronger bond. And here one might argue hard soft type argument to explain why it lies off of this line to the 2p second better show elements. But then it's still a puzzle with hydride. Hydride always seems to be stronger than this correlation would predict. That is to say, just guessing at the metal hydride bond strength from H8 bond strength, when it comes up always short. That is, the metal hydride bonds are always 5 to 10 kilocalories per mole stronger when we guess based on this correlation. Then finally, most recently, Bergman, together with Kevin Peters and Carl Hoff, have tabulated a large number of bond strengths for rhenium hydrides and alkyls. With Peters, they got a benchmark number using photoacoustic spectroscopy, where dikenyl peroxide is photolyzed to give this oxygen-centered radical, which rapidly extracts, in this case, the deuterium atom from the iridium dibutyride. That reaction produces a heat wave, an acoustic wave, with which is correlated to the enthalpy of the process. And for those kinds of processes, the known OH bond strength, the butanol, they estimated a bond strength for the iridium hydride of around 73 kilocalories per mole. Again, very respectable bond. Using that as the benchmark with some calorimetry they carried out with hydrogen chloride and carbon tetrachloride on these compounds, they were able to tabulate a number of bond strengths from neophenol, which is weak, probably for steric reasons, all the way to phenol, which is a quite strong bond. And here I've just shown at the bottom that if one sums up the iridium carbon and the iridium hydrogen bond, subtracts the CH bond, you can see that these carbon-hydrogen bond oxidative additions I talked about early on are thermodynamically really quite favorable, 30 to 45 kilocalories per mole downhill to oxidative reaction. And finally, our group has used these single bond metathesis processes to get relative bond strengths for early transition metal hydride, alkyl, and aryl, and alkyl bonds as well. Using these equilibria shown here, and in some cases resorting to intramolecular type trapping to shift equilibrium to a measurable extent to one side. Notably, the alkyl bond is stronger than one would anticipate based on my correlation, and in fact it can't affect this process even by attaching a benzyl group to a cyclophenoldiene, and this equilibrium lies way to the left. You can tabulate these results as I've done here, ordering in a vertical scale the alkyl hydride HH bond strength, benzene CH bond, and the alkyl bond strength. And you see that the same order holds for the hafnium and the scandium systems, with two exceptions. One is, again, the hydride is out of place. Here, the metal hydride is stronger than the correlation based on the analogous hydrogen to carbon or hydrogen to hydrogen bond strength. And the other big difference is that the difference between these bond strengths is larger for the metals. Another way of saying it is that whereas a carbon-hydrogen bond responds favorably to an increase in S character at the carbon center, the metal carbon bond responds even more rapidly. So that the alkyl bond strength is tremendously strong here, and the aryl-alkyl difference is much larger than you would guess based on this correlation shown here. The exact reason for that's not clear. We originally thought that might be due to a very ionic bond. Indeed, S character would favor an ionic bond because that makes the carbon more electronegative. But that doesn't seem to be true. We've tested that concept with experiments, and we really are at this point puzzled by the fact that these differences are larger than the correlation with the hydrogen-carbon bonds. And that seems to be true not only of scandium and these early metals, but also the late metals. Bergman found the same thing in his iridium study. So we still have some way to go in understanding these processes. Okay, let me summarize by pointing out what I consider now to be the basic transformations in organometallic chemistry. We've had these concepts of ligand association to generate the reactive metal center around for a long time. They still, I think, are central to many of the reactions. Getting the ligands off to generate a vacant orbital on the metal is crucial in many cases. In recent years, organometallic chemists really haven't used these external attacks by nucleophiles and electrophiles to the extent they were early on. Certainly, those interested in applying organometallics to organic synthesis routinely take advantage of these kinds of electrophilic and nucleophilic attacks on ligands of organometallic complexes. The oxidative addition reductive elimination sequence has now been expanded beyond hydrogen halides, alkyl halides, and to carbon-hydrogen bonds. We know more about H2 now. And one thing that I'd like you to think about is that, at least in these cases with H2 and CH, a sigma complex almost certainly mediates these reactions in both directions. Alpha processes are now being explored not only for carbene hydrides and alkyl carbenes, but also for systems, and also certainly for carbonyl-ions and nitrile. But now for these heteroatoms like oxygen and nitrines and sulfur, where these processes can affect either formation or breaking of the bond with a YZ double bond, olefin insertion, metal hydrogen bond, beta hydrogen elimination certainly fits that. But now there's more and more interest in the case where X is carbon, and of course that constitutes the propagating step in olefin polymerization. And that fundamental step is under intense study. Many more examples are now cropping up in the literature. Olefin metathesis is certainly represented well by this basic process shown there. And I hope you've seen that ring opening metathesis polymerization is a very fruitful way to take advantage of that fundamental transformation. Sigma bond metathesis is non-redox way of activating things like CH bonds, H2, and the like. Has now been widely found with metal centers that are electrophilic, early transition elements, lanthanides, actinides. And indeed, these are very facile processes, despite the fact that they must go by some mechanism other than oxidative and reduction processes. And finally, this process is involving the last member of this set of permutations, namely the null X double bond with a YZ sigma bond, single bond. I think that's really the reaction of the future, at least I'm banking on it. I think the metal oxo and the metal amido reactions with things like CH bonds might really be possible if one can get the metal center electrophilic enough in an ion oxidation state. And that might, in fact, turn out to be the best way to affect functionalization of hydrocarbons. Okay, it remains for me to simply thank our research group. Some of them are shown here. A number of them aren't. One of the best things about being in a place like Caltech is the wonderful group of people that are available to work with you.